All right, so that's chapter 7 in a very brief nutshell. You can read it. I would read it at some point because I think it's still interesting stuff. And there's more than just coronal potentiometry in there, but that's the basic idea. Let's, how are we doing on time? I think we've got time to start this. Let's start it back in chapter 10. The idea is here with bulk electrolysis. And the reason we're talking about current first is that we sometimes use constant current methods in bulk electrolysis as well as constant potential methods. So that's the idea. Now, you know, often in the point of, as I said in the notes, the point of all the experiments really previous to the now, the point of doing the electrolysis was only to get a measurable signal. We did electrolysis to see a current flow that will give us a signal to measure. And so we really didn't want the electrolysis to change the concentration of the species in solution. We wanted them to stay at the bulk level so that we had a baseline. In bulk electrolytic methods, the focus has changed. We want to actually use electrochemistry to cause a change in the overall level. Why would we want to do that? One thing is if we want to provide increased analytical sensitivity. If we have a very small amount of material in some system, perhaps a way to increase the sensitivity is to use all that sample that we can, electrolyze all of it, to increase the sensitivity if we have a very tiny amount, rather than just a small fraction of it like we normally do. The other major reason is if we're doing some sort of electrosynthesis methods. We don't want to synthesize really tiny amounts. We want to synthesize as much as we can, and that means transforming as much of our starting materials to products as possible. So we want to maximize our ability to do that transformation, and that relies on what we call bulk electrolysis. By doing a bulk electrolysis, often we can examine chemical reactions. For example, one way to study what happens when we do, say, a reduction process and then with an accompanying follow-up reaction is to do a bulk electrolysis. Let the reaction occur and then do some other method, let's say chromatography, to analyze the products. And so by doing bulk electrolysis, we can do the whole system, study the products, and get some information about what's going on. A fourth thing that we want to do is separations. We can use electrolysis to separate two or more different things. By electrolyzing one component of the system or some of the components of the system, we can effect a separation between the two things. The important thing with all these types of methods is they're all characterized by large area to volume relationships, where area is the electrode area, the volume is the volume of the solution. So unlike what we've done in the past where we've made the electrode area very small compared to the volume, here the goal will be to make the electrode area as large as feasibly possible while minimizing the volume of the solution so that we can do our electrolysis as efficient and as rapidly as possible. So large electrodes, large voltage, large currents. Instead of microamps and nanoamps, we're talking about amps and milliamps, sometimes kiloamps of things, so large values of these things. These are what they're not, definitely not what they'd call microelectrode techniques. Remember we said there is kind of an old-fashioned use of the word microelectrodes to refer to electrodes of centimeter size and so on. These are electrodes that are of meter size and maybe, and so on sometimes. So anything bigger than a centimeter and so on often would not be microelectrodes. Now there's as I said, there's two ways of doing this. One is, as we've already examined a lot of the ideas previously, in using controlled potential methods. And these are nice, especially for smaller scale bulk electrolyses. In other words, we're doing sort of bench scale reactions where we can use reasonable amounts of currents and voltages to do the reaction. Now, a lot of times the difference between these larger bulk electrolytics processes and the analytical processes that we often have to be much more careful about cell designs and layouts. Because the currents are larger, we have more IR drop possibilities. We have problems with maybe solution heating. We have problems with using perhaps larger voltages and larger currents, which means safety problems. We don't want to electrocute ourselves when we're doing these things. And so we want to be very careful about cell. For example, let's draw a little bit of a cell that you might use that would not be necessarily the ideal cell, but gives you some of the ideas of the problems. You might have a mercury pool as our working electrode. So you hear right away, you've seen it's a big, the bottom of the beaker is covered with mercury, so that's a big electrode, a few tens or hundreds of square centimeters. The auxiliary electrode often is in a separate compartment, separated by usually a glass frit. Why is that? Well, remember, whenever we do a reaction at the working electrode, an equal and opposite reaction has to occur on the auxiliary electrode. The same amount of current has to flow out of both electrodes. So if we're doing a reduction at the mercury, we have to do an oxidation at the auxiliary. If we're doing a large fraction of the possible of the system, that means there's a lot of products being formed at the auxiliary electrode. And what we usually do not want to have happen is the products of the auxiliary reaction diffusing into the working electrode compartment and causing an interference. And what that would do especially is causing interference that would change with time. So for example, suppose we're doing a reduction. A common process here might be, we might be making oxygen gas at the auxiliary electrode, or even something like chlorine gas if we had which would be not ideal. Usually the oxygen gas would be bubbling off. The pH would change dramatically in that compartment. It would go very low values, and this would cause the pH in the, so we don't want to mix those two compartments, keep them separated. So we have a frit here to do that. So frit allows the current to flow between the two electrodes, but not allow a solution to be mixed. Sometimes we put in what they call a depolarizer. Some solution species that's easy to oxidize or reduce, and that minimizes the overpotential required at the auxiliary electrode. And so instead of making oxygen gas, you might just make some reaction occurring in that as a useful way. Instead of having a working electrode just in solution, often what they have is what they call a Lugen-Haber capillary. You'd have a reference electrode here, and then a capillary, or a tube with a very pointed capillary end. L-U-G-I-N-H-A-B-R, capillary. The idea is that, again, remember how we talked about the reference electrode senses the working electrode potential. Because there's a large amount of current flow, the potential drop can be quite steep. And so by putting that capillary very close to the working electrode, we can measure as accurately as possible that potential drop and correct for it. And then usually in systems like this, we're often stirring the solution, so you'll have in there a stir bar. A stir bar helps to minimize the diffusion layer that develops and keeps the reaction going at a reasonable rate. So we need to keep the auxiliary and working electrode separate. We need to have a good, stable reference electrode because this reaction may be occurring for days, although that's unusual, at least an hour sometimes or more. So we don't want the reference electrode potential to be drifting around while we're doing an experiment, so that if we could drift into a potential where we don't want it to be. We also need to have good, effective stirring. Now this is a fairly small and probably actually a very inefficient bulk electrolysis cell, but it's a simple one to make. Also the problem with the potentiostat is that we need to be able to supply high currents, and And we also, in order to supply high current, sometimes we need to supply high voltages to do that reaction. So potential stats for bulk electrolysis often have 100-watt or even 200-watt capabilities. They can supply large amounts of voltage and current to do it, which means they're actually quite lethal if you're not careful about using these experiments properly. The other important different type of experiment is so-called controlled current methods, as we talked about. The idea here is rather than trying to control the potential, let's just go ahead and put current through the system at a controlled rate. And it's not as accurate as, the problem with the controlled current method is you have to be very careful about making the current just right so that you're only electrolyzing what you want and you're not shifting over with your current and electrolyzing something that you don't want to see. For example, you only want to have enough current to do this reaction, not so much current that you're doing this reaction. But for big industrial processes, it's often a very efficient way to do this because, for example, it's very difficult to make a potentiostat works that may be required to supply, say, 1,000 or 10,000 amps that you might be using in a cell for an aluminum electrolysis process or some other process. So you want to use a constant current mode. It's easier to supply these sorts of high currents. Not easy, but easier. And as I said, you have to make sure that you're not shifting the current. You have to have a right amount of current so you're not shifting into making side reactions also, when the reaction is complete, it's difficult to know exactly from the constant current mode. But as I said, in an industrial setting, that's often easier to do than setting up a high current potentiostat. Much cheaper, generally. Okay. All right, well, let's, how much time we got left on that tape, Rob?
16 minutes.
Why don't we stop here and we'll take a very short break and we'll continue to talk about the test after this.